Hello. Hello, yes. Good afternoon. Welcome to this lecture. Maybe many of you or maybe some of you knows me from previous course. I was giving another course, circuit analysis. Maybe some of you knows me, but I have one slide about myself. Yeah, I copied from one of my previous course. I'm Muhammad Amin. I'm called Amin, so you can call me Amin, just Amin. And I am an associate professor here in the Department of Electrical Engineering in the field of digital control of power electronics for cyber physical system. So this means I work power electronics converter application to many systems, including renewable energy system like solar, wind, battery, and also machine drive. This about a little background about my education. I did my PhD from here and NTNU in 2017. I finished it. And then I was also teaching some other courses before, but now I don't have the responsibility of many courses. Now I focus mainly on research and teach now this course, Drive, this year, part of the course, and also another specialization course. Yeah, so I also talk about a little bit about my research background. Yeah, I focus many things, power electronics, application to power system. And recently, I'm also focusing application of different AI technology for power electronic system. So this is a brief background about myself. And then we can go back to the lecture today. This lecture, we focus on controller and the filtering in machine drive. So the main focus of this lecture will be application of controller in motor drive and also filtering. I will not cover the filtering part today. I will mainly focus on the controller part today. So what we have here, yeah, I forget to mention that if you have any question, just feel free to interrupt me at any point. Just raise your hand or ask the question directly. So if we talk about the controller in a motor drive, in a machine drives, and if we look at the different books and the research articles, there are many different control. The most classical one, simple controller, is the PI, or PID controller. P, proportional controller, PI, proportional and integral controller, or PID, D for the derivative. PID, proportional, integral, and derivative controller. There are many other advanced control systems like model predictive control, sliding mode control. They are based on the advanced mathematics. In this course, we will not focus those advanced controller. We only focus on PI controller, and we can see that the proportional and integral. This means we have to find some parameters that makes our drive operate optimally. So we will check then how we can find those parameters here. And also, previously, the controller, they are implemented in analog devices, analog electronics like operational amplifier. You know that we can use operational amplifier almost for every mathematical application like integration, low-pass filter, summation, subtraction, all these things we can perform just using operational amplifier. So we can use the operational amplifier to design the control system, but now we don't use operational amplifier that much for designing the control. We still have the operational amplifier for other purpose in the motor drive, like the signal conditioning, scaling, filtering a little bit. We use the operational amplifier there, but the main control now we use in the digital processor, like microprocessor or FPGA, which can operate very fast, almost like continuous controller, and also we can use all the sophisticated control program inside this microprocessor. So we will check how we can implement this controller also in the processor and the microprocessor. And there are different methods of tuning the control parameters, like we check the location of the poles, where we try to put all of them in the left-hand side of the XY plane. And also you can check the board diagram, the frequency response of the transfer function, and we check the gain margin and the phase margin. That's one way. And the other way to use modulus optimum and the symmetrical optimum. So in this course, in this lecture, we'll focus on these two methods, modulus optimum and the symmetrical optimum method, how to tune control parameters using these two concepts. Yeah, and also this lecture, not today, we will also be familiar with the ripple that generated in the motor drive, and then how we can choose filter to filter out this ripple component from the control system. So let's talk about the control system for a motor drive. So we can see a general motor drive, how it look like. We have the motor, and then, yeah, this is an AC machine, induction machine, PM machine, or any kind of machine, AC machine. Then we have this structure. Here we have the grid, where we connect our machine, and then we have this drive system, and then we connect the machine here. And you will see some of the machines, they are connected directly without having this complex system, their direct connection to that, and then it operates some particular operating point. We cannot have the opportunity to control the frequency, control the speed, torque, all these things. But if we have this configuration, then we have better flexibility of controlling the machine. So almost all the industrial drive that you will see that you could have this structure. And we have one converter here and then another converter, and this one is the rectifier here. So you have the AC input, and then it rectifies to DC voltage here. And this could be controllable rectifier or maybe uncontrollable rectifier. So you know, controllable rectifier means it could be IGBT-based control system or thyristor-based. If it's uncontrolled, just simple diode rectifier here. So we could have anything controllable or uncontrollable, which provide a constant DC voltage here. So if we have a controllable, then we also need to implement the control system here that provide a constant voltage here, DC voltage. Here I just wrote a control unit. And when you have the control unit, and it could have some inner controller, inner loop controller. Most of the cases is a current controller, inner loop controller, and then outer loop controller. So it's like we have the inner loop, which is the current controller, and then outer loop, we'll have the DC voltage controller. Then this DC voltage controller gives the current reference here, and then you have from the current controller, we have the controllable voltage. So we have this. And then we generate PWM signal here. How we generate PWM signal? We provide this controllable voltage, which could visually sinusoidal signal. So this EU is a kind of sinusoidal signal, and then we compare with a triangular wave. So we compare with a triangular wave that give us PWM signal. This PWM signal tells us how long the IGBT or the MOSFET should operate. And that gives us the desired output voltage here in the DC link. So this is about the grid side converter. But in this course, we will not focus that much on the grid side converter. We will focus mostly on the rotor side, machine side converter. But even though if we focus on the machine side converter, but the control structure more like the same. Like what you see here, we have the direct torque control, and inner loop is the current controller there. So you have the current controller, and you will get in the next few lectures, we'll present more detail about this current controller. But today, I'll present basic how you can tune this inner loop current controller or outer loop voltage controller. In this side, here you have the inner loop current controller, and the outer loop is speed controller. So what you see here in the inner loop, we give the current feedback. So we have the sensor here that measured the current that's going through the motor, and then we feed it here, and we compare, and we control it here. And then in outer loop, we are providing the current reference from the speed controller, and then we have the speed sensor that measures the speed of the machine. And then this is the reference speed, like this is the speed that we want. You can think about the simple example like in your car, electrical car, that you have the desired speed, 90 kilometer, 100 kilometer. When you set your cruise control, then you give some speed and it always maintains. So this means it has some internal control there that keeping the speed constant. So in this lecture, we'll discuss how we can tune the parameters of this control. Just it's general overview, not in detail inside. In the next few lectures, you will know how to go more in detail. Any question up to this? And we are also saying a lot about this operational amplifier. And we have the voltage sensor, for example, here, that measures the DC voltage. There are many different types of sensor, like Hall effect sensor you can use. And then this voltage, we cannot directly send to our microprocessor. Like some microprocessor, maybe they can take up to 5 volt, 0 to 5 volt perhaps. But here we might get a bit higher voltage, so we might need to do some scaling, level shifting to process it here inside the controller, microcontroller. So that would be the topic, how we can control. Now we can talk about the control structure. If we look at the control structure in the previous slide, where I show a motor drive system, and we see that in the control program is contained two main things. One is the sequence. Sequence means which one should operate first and which one should operate last, like this. It's like here. So you can see there are many components, like we have a breaker here, or relay, and we have the capacitor here, and we need to establish this voltage. So which one should operate first? Like maybe we would start operate this one, then it will supply, then we will get the DC voltage. When it reaches to constant DC voltage, it takes some microsecond or millisecond to get the desired voltage. Once it reaches to that, then we will try to operate the controller and then operate and turn on the PWM. So this means we have the many things that should operate there, like a flow chart. This means you have something and I start from here, then once it yes, then it goes to the next state, and other when it's not yes, then it should come back to here or maybe there. Like different mechanism, different flow, different logic. So the first part is to define the state machine, which way and why, which position it should operate. So once we have the state machine running, and then it will check when it satisfied all the condition, then it will start running the controller inside. This means when it's satisfied, then it will operate this control, and when it operates the control, then it can turn on the PWM. So we have also inner logic that will turn on the PWM. Once it's turned the PWM, then you can control the voltage, speed, current, and all these things. So we have to define the detailed state machine. Maybe in this course, I don't think you need to define or design the detailed state machine, but it's good to know that it has this state machine, all the detailed logic. So once you have this detailed logic, and then this can be used to operate the relay, cooling fan, and all these things there to enable, disable for different scenarios. So once you have this, then we'll operate the control loop. So in the control loop, we have the different controller. The most inner one is the current controller. So most of the power electronic system or the drive system, you will see that we have the inner loop current controller. And in the outer loop, we will have the speed controller, maybe position controller. So they are cascaded. So you have the first one, inner loop, and the next one, the speed control, maybe then the position control. So they are connected, they are cascaded. Like the inner loop current controller, it gets the current reference from the speed controller. Maybe speed controller sometimes gets some reference also from position controller, or maybe it gives direct signal to the current controller. How you're defining the system. So you have the sequence control or the state machine, and then you have the control loop. Once you have the control loop, then it's the time to decide what type of controller to use for this particular application. And I was saying that there are many different controls. The most classical one is the PI or PID controller. There are other like model predictive control or the sliding mode control. So those are advanced controller and will not be the topic of this course. So here we'll focus on mainly PI controller, and the PI controller is good enough to track, to perform the operation that we want. Like some other cases, like if you consider an airplane which has the electrical engine instead of the traditional fuel-based engine, this means it has a motor that running there. And depending on the controller, and you will see that the PI controller may give you response something like, when you change the speed, then it might give you the response something like this. So what does this mean? We want the speed at this level. This means it goes a bit high and a bit low, a bit high, a bit low, and after some cycle, then it settles to a certain point, at the desired point. But if it's an airplane, then we don't want it to go fast and slow, go fast, slow. So we don't want this type of behavior. And how we get the desired behavior is based on the tuning parameters. So if we tune the controller parameter, or if we use the proper controller, then we should get the response, something like the green one. For example, if we tune the PI controller a good way, then it can also give us the response something like this. Not exactly like this, but closer to this one. And if you use the model predictive control, MPC, that can give something like this. This means it's very smooth. But for simple industrial application, we don't need like this in industry, a simple industry, then we don't need this type of response. They're quite okay having some sort of a little oscillation. So most of the industry, they use only PI controller, and it gives the performance that we want. So here is an example of a PI controller, how it can be implemented in Simulink or in a DSP or in an analog controller. This is the one designed by Roy, Professor Roy. And what you see here, we have the many different components. Okay, so first we need to understand what is PI controller or PID controller, how they look like. Maybe I can draw one here. So I was saying that we have a reference signal. This is our reference signal. This means this is the one that we want. And also we have a feedback signal, or we can say it's a measured signal, and this is measured. And we subtract it. When you subtract it, it gives us the error signal. Then when it's a proportional controller, then it's only KP. So this is only P controller. We have only P controller. And when we make it as a PI controller, then also we add an integral term there. So how we add the integral term? From here, we have the integral gain, Ki, this Kp is called proportional gain. And here we have the Ki, which we call integral gain. And we put the integration. In Laplace, we put 1 over s. So that is the integration. And we add both of them. So this is the output that we get. So this is the PI controller, one way of implementation. And if it's also possible to make it as a PID controller, if you want to make it PID controller, then what we need to have a derivative term here. We put the KD as a derivative gain. And there are many different ways of implementing this derivative controller. One way is to put something like this. So we have the derivative the S as a derivative, and also we have a filter, 1 plus Ts here, one low-pass filter. So this is one way of implementing the derivative controller. So now we have this PID controller. First we started with P controller, then we make it PI controller, then we wrote it as a PID controller. So we can also see that here for the PI controller, and we have the Kp plus Ki over S. This can also be written as Kp. We take the Kp common, and then what we have 1 plus, we can write it 1 over Kp over Ki. And here we have S. And we can write Kp over Ki is called the integral time constant, which is Kp over Ki. Then we can put it this term as a Ti. Then we will have Kp 1 plus (1 over Tis). So it also can be presented like this way. And then if you want to simplify a bit, then you can write Tis 1 plus Tis. So that's an PI controller. So you can write also the transfer function of a PI controller like this. So you can see in this PI or PID controller, it's just you have the reference signal and the measured through some sensor, and then you got the error signal, and it goes, and that gives us output. This is a simple way of presenting a PI or PID controller. But in industrial application, in addition to that, we also put a lot of things. What are those? Those are limitation, initial value setting, feed-forward, anti-wind-up. So I'll discuss a little bit what that mean. Here, the limitation. So what we are saying that when you have a controller, like if you say speed controller, we have measured speed and we have the reference speed, and it passing through a PI controller, that gives us the current reference. So we are getting a current reference. If we have a motor, let's say this motor can take maximum 100 ampere. If it's more than 100 ampere, then it's too much, then overheat, it will produce more heat, then it will destroy the motor. So what we can do that, using a limitation function, we can limit the current. We can put the maximum 100 ampere when PI controller give 100 ampere max, 100 ampere, more than 100 ampere, then it put the limit that the output should be 100. Even though it's giving higher, but it cannot, because like if a motor can have some particular torque, and it cannot operate more than that torque. This is the rated torque. So we put the limitation that even the PI controller give higher torque reference, but we put it to this limitation that this is the rated torque. It cannot be higher than that. So therefore, we put a limitation function in a PI controller. And the next one is the initial value. We have an integrator. We can set the initial value, what will be the output of the integrator. There, we can set an initial value. And also, we can set an initial value for the output of the controller. So you have the PI controller. We can set an initial value of the controller that it has this initial value. Then when we turn on, then it will put this value. Before starting integrating, it will provide this value. And then here we have two other values, the upper limit and the lower limit. So we set the upper limit and the lower limit. Like if it's a torque, then we set this is the maximum torque, and this is the minimum torque. Or if it's a current, then this is the maximum current, this is the minimum current. If it's voltage, this is the maximum voltage, this is the minimum voltage. That we set. Like, for example, if it can take up to 220 volt, then if the controller gives 250 or 300 voltage as a reference, then we said that even though it's giving 300 voltage as a reference, but we set it to 200 or 220. So we set the upper limit and the lower limit here. And then another we also implement is the enable block. Sometimes we need to disable the integrator because when it reaches to maximum values, then there is no point of integrating the error. So if we continue integrating, then it will give more higher value, more higher value, more higher value, but we have the upper limit and the lower limit. So what it do that, it disable the controller, it disable the integrator so that it stop integrating, so that when it come to return to within the limit value, then it can again start integrating. And another one here, you'll see that feed forward. And what is the feed forward means? Sometimes we have some disturbances. We can either measure this disturbance or we can estimate the disturbance. So we need to put also this disturbance in the controller so that it can cancel the effect of this disturbance. This means we have this disturbance and then we are measuring the disturbance and put 180-degree phase shift of this disturbance so it cancels the disturbance. So we put feed forward term to cancel the disturbance. And another one also is called anti-wind-up. There are many different ways of implementing this anti-wind-up, but the main function is to limit the integration. When it reaches to saturation, maximum or minimum limit, then we try to stop it, try to reduce the input so that it comes back to normal value, and then it starts the integration. So those are the functions that we usually implement when we design the industrial PI controller. So this is one example here we have in the PI controller in Simulink is a continuous. Roy designed it in Simulink. So I'm presenting it here. What you see. First start with, we can remove this feed-forward term. If you remove this feed-forward term, let's say if you start it here from, and then it's sending the signal through this to output. So the first line, it was saying here, is only proportional controller. You have only the KP. Here we put the KP1, but it's the KP that we can find based on the tuning, modulus optimum tuning. So you have the PI controller. And then in addition to that, if we pass it through this integrator, and we add it here, and then it's PI controller. So now we have initially P controller, then we have this 1 over Ti is the integral time constant, and we show that we can present the Kp, and then integral part we can write also 1 over Ti, integral time constant, and we have the integrator, and we sum both of them there, And that gives us the PI controller. And the first one here on the top, we say this is the feed-forward term. We usually put the feed-forward term to 1. This means 1 means you're feeding the disturbance. And if you put it to 0 there, then we are stopping. We are not sending the feed-forward term. So you have this feed-forward term here with 1. And then what else we have? We have the limit here. So when it reaches to upper limit, then it will send only the upper limit signal. And when it reaches to lower limit, then output will be the lower limit signal here. And when it reaches to upper limit and lower limit, and also you are sending the signal to disable the integrator, because when it reaches to the level, then there is no point of continuing integration, because it usually cannot send the output because it reaches to limit. So we are disabling the integrator here, and then when it comes back to initial point, then it can again start integrating. So we have also initial value, and we can set the initial value either directly here in the output, or we can also set the initial value here in the integrator. So we can set the initial value of the integrator, and we can set also initial value of the output. And another thing we have is the enabling the integrator. This is the enabling part. This is a signal. When it 1, then this means here we can enable the integrator, that it comes the signal here, and it continue integration. And when you put 0, this means it's a stop integrating, and it sends the output signal, which we feed forward here, the initial value function that it got. So this is one standard way of implementing implementing a PI controller in industrial process. When you have the machine drive, then you usually have this type of controller with all the function, with the feed forward. You must have this limitation function, feed forward function, initial value function, enabling function, all these things. So this is one of the standard way of implementing industrial PI controller. Any question here up to? So now what we see that we have the controller, and the controller has some parameters. If it's a proportional integral PI controller, and we see that we have the 2 parameters. One is Kp or Ki, we can write that way, or we can say Kp and Ti. We present it in 2 forms, like one way we see that we can write it Kp plus Ki over S, and this is Ki. So we have the 2 parameters, this is Kp, Ki. We also can write it like this, 1 plus Ti S Ti S. So yeah, they are same, equivalent, and we know that Ti is the Kp over Ki. So we have the 2 parameters, the Kp and the Ki, and we need to tune. We need to find the value of these 2 parameters, Kp and Ki. So how we can do that? If we don't have this proper parameter, and it will not follow the reference that we want. It will not follow the speed. I think you will disappoint that when you ride on your electric car and you want to ride to the speed of 100 kilometer and it run with a 50 kilometer speed, you will be very disappointed, right? So you need to find the optimum parameter that give you your desired speed that you want. So there are different methods that you can use to tune this parameter, more advanced methods also. The most commonly that we check the board plot, and we try to have the gain margin at least 6 decibel. So this is the gain margin that we want to have. And also you want to have the phase margin 45 degrees. The higher, the better. But this is the minimum that we want to have. So this is the one way that we check whether the total transfer function, the process, they are in a stable condition. And then we also check the location of the poles, whether they are in the right-hand side or the left-hand side. So we try to keep them always here in the left-hand side. And we know that if anything in the right-hand side, right half plane, they are not stable. This means they are not give what we want. So you can use also location of the poles, and we set the location of the poles, and that give us some, after some iteration, what will be the value of the controller parameters. And the other way of tuning the parameters is using modulus optimum tuning method and the symmetrical optimum tuning method. So in this course, we'll focus these two methods, modulus optimum and the symmetrical optimum, and we also present the board diagram, how they look like, what will be the process of having different gain margin and the phase margin. So now we can start with a system. Here we have the closed loop system, this figure I'm talking about. And we have the reference, it could be current reference or the speed reference. And here output is the real speed. What is the speed? I said the 100 kilometer per hour, is it 100 kilometer per hour or not? So you have the input and reference, and we have the output. And what you have here is the error signal. And it might have a lot of harmonic signal, not harmonic, ripple, like a lot of oscillation, and we don't want to feed this oscillation through the controller. So we have a filter here. This is a filter transfer function. Mostly we use low pass filter, but there are many different types of filter you know. I think you learn. But consider a low pass filter here. So you have the controller transfer function. If it's a PI controller, then it's the proportional integral controller transfer function. And you have the process transfer function. So what is process transfer function? Like if you have a machine, and the machine has something input and something output. Like if it's a DC machine, then what you are giving the voltage, and then you are getting the output as a torque or speed, whatever. So this is the speed, this is the voltage of the machine, and then you are getting the torque or maybe speed, whatever. So the transfer function between these two input and output, that is a process. So you have the transfer function of the machine, and you have the transfer function of the controller, and we pass through the filter, and we are comparing here. And in addition, we have also one term there, the disturbance, some additional, like if it's a DC machine, and we know that DC machine has some induced inner voltage, that can behave like a disturbance. And if we don't have properly tuned the system, then disturbance has a lot of effect. So we try to tune the control such way that the disturbance cannot make any effect to the system. So let's check how we can tune, or what would be the impact of each of the parameter. So first, I start with finding the open loop transfer function. So what we say the open loop transfer function, we have the loop here. This is the loop. Here it's going this way, and it's feedbacking here. So we have this loop, and the first step, we open the loop at this point. When you open the loop here, then what you have the open loop transfer function is this part, multiply with this, and then this. So this is now. We have the open loop transfer function. So this is the open loop transfer function that we get here, H naught. So we got the open loop transfer function, which is the controller, their process or plant or machine, whatever, and we have the filter. So this is how we got the open loop transfer function from this to up to here. And then we are checking about the closed loop transfer function. And what is the closed loop transfer function is the ratio between output to the input. So we have the output here, which is YS. and the input, which is yref. And here we have the error. And what is this error? Is the yref minus hf multiplied with ys. So you have this input there, yref minus href ys multiplied with hr. And if you rearrange and neglect this part, and you'll find the closed loop transfer function. So I believe you have the good background on the control. You have the control course, so you know how to come to this part, getting the closed loop transfer function. So we have now the closed loop transfer function, and here you can see that we have this 1 over hf, and if you look at this part, h naught 1 over h naught divided by hf, which is actually these two terms, hr multiplied with hf. If you look at here, is h naught divided by hf. This means hr multiplied with heu. So now we get the closed loop transfer function. And you can see that if we look at the low pass filter, and let's say it's more like 1, this means what we are giving in the input. If we consider that it doesn't have any ripple, this means what you are giving input and you are getting the output. So you can see that the output y depend on the open loop transfer function. So now if we want to look at the frequency response of the open loop transfer function, now look at the frequency response of the open loop transfer function h. What you will see, I can draw one figure, something like here. And you will see that the frequency response in a board diagram, something like this. So up to this point here, we have this is 0 dB at this point. If it's 0 dB, and we have, this is we call the cutoff frequency or crossover frequency, omega c. So what we see that from 0 to omega c, the frequency, and we see that h omega has a higher value. This h omega is dominant here. It has a higher value. So what will happen if we have the h omega higher value? Then you can look at this point. So you have the h omega, which is a large value, and you have the 1 plus h naught, sorry, not h omega, is h naught, and 1 plus h naught. Since h naught is a large value, it has a large value, so we can write 1 plus h naught is equals to h naught, because we can neglect 1 here, because this is the very high value. So what give us, when it, in this condition, we are getting 1 over hf, because this h naught is cancelling h naught here, because it's very high. And what you see here is 1. So this 1 mean here we have 1. So we are getting output which is the same as the reference. Right? What we are getting, now we have the m, which is 1, which is y naught or ys over y ref. This means we are getting ys output, which is the same as the y ref. And we are getting it only for this condition when h naught is higher than 1, when is a larger value. So this tells us if we have the higher this value, then we get the good tracking performance. So what we are setting in the input, then we are getting in the output, because we have very large value here. Usually in a PI controller, we have something DC input, like if it's speed, then it's not going from plus to minus, it's staying in some DC values. If it's current, and also we are putting it a constant DC value. Maybe you're not familiar with DQ value. If it's a 3-phase ABC system, then you can convert into DQ system. In the DQ system, this ABC quantity, the sinusoidal quantity, you are converting into DC value. So once you have the DC value, this means you have very high gain here. When you have very high